Hello ladies and gentlemen. Today we're going to be talking about AC signals, and we consider sine waves. And why isn't my ink there? So I got myself a Wacom tablet. Doesn't make those clicking noises whenever I use the pointer, so that's kind of nice. We're going to get into complex numbers. The complex constant I equals the square root of -1, J equals the square root of -1. I in electrical engineering is a symbol used for current. So electrical engineers gravitated to using J to mean the complex constant. Instead of I, we use J. Just makes it a lot easier. Okay. Phasors. A way to think about complex numbers. A shorthand notation. New terminology. Impedance and admittance. Phasor diagrams. The way to get equivalent circuits. And then we can analyze using complex numbers. Kirchhoff's laws are applicable, and other techniques, node, loop analysis, etc., are all applicable. So we're going back to what you know. We're trying to build mathematics that builds on what you already know. Just need to add some new things. Another thing, what is this good for? Why don't we always just use AC circuits? Oh, excuse me, why don't we just use DC? Why are we even fooling with AC? Well, if you're into power electronics, power transmission, this is necessary. It's how our entire electrical grid works. Even if we go to DC transmission, that's a thought, transmission over wires that are megavolt DC, the transmission is more important. You have less loss, less power loss, less wattage loss, less energy loss if you use DC, high voltage DC. The trouble is, you got to get that high voltage DC down to low voltage DC, and that takes AC. There's AC in the middle. A brushless DC motor, they take a DC input, they convert it to AC, and it's the AC that actually runs the motor. And if you have a sensitive sensor, a strain gauge, for example, and you have a shaft, it's in a noisy environment, a lumber mill maybe, you got to build sensors that run with all that sawdust and sound and vibration and electrical noise. Motors, big motors, you know, they have coils in them, and they generate pretty big magnetic fields that can be picked up by sensitive electronics. So, like your radio, you can encode a signal using a very specific AC frequency. And then the environment might have a whole bunch of other frequencies and noises and things like that in the environment. Then when you get to the receiving circuit, you can use other circuits to tune right into that frequency you send it at. Just like radio, or your cell phone for that matter. There's a little tiny radio in your cell phone that there's a ton of electromagnetic signals in the environment, but your radio or your television or your cell phone picks just one of those. So, and for sensing in noisy environments, for you mechanical engineers and other engineers, etc., this is something we need to do. Okay. How does it work? Sine waves. Eventually, we're going to get to the point where people think of cosines. not sines. But this helps illustrate what we mean by phase angle. And we start out with the plain old sine function, like so. And this is the radians. Radians on the x-axis. And of course, this is the magnitude. This would be the amplitude of your sine wave, xm, amplitude. This is the time domain. So omega, the frequency, is in radians per second. So we can look at things under the time domain or excuse me, under the angle domain or the time domain. Sometimes the angle domain is more useful, by the way. Get on with it. So this just says what I just finished with. The period 2 pi radians, or omega t has to equal 2 pi. Here's omega t. One full cycle is 2 pi radians. So that means the period is given by this equation here. Okay, this is another important thing, that your signal in one interval, in the interval from 0 to 2 pi, is the same as the signal in the interval from 2 pi to 4 pi, and so forth, and also backwards from 0 to negative 2 pi. That's what this formula is expressing. It's trying to tell you. Same thing with radians, that the signal in radians, or yeah, 2 pi, 4 pi. The same thing with time, that if you add one period, the signal between 0 and the period is equal to the same signal from one period to 2 times the period, or the same as the period from negative capital T to 0, capital T here, to capital T. That's what this is trying to tell us. Okay, let's see, more formulas. We think of frequency, how many cycles per second, one cycle per in this many seconds. So we can get the frequency in hertz. Hertz is a unit for frequency, by the way. Radians per second, that's angular frequency. This is the phase angle. Theta is the phase angle. That this wave starts before, the gray wave starts before the red wave. And because they're using red all the time, I'm going to change the color on my ink. There, I'll change it to blue. So it leads. It happens before. When you have a phase angle that's leading, theta is a positive number. And I think of it, what does t have to be, little t, what does little t have to be to make this 0? Well, little t has to be negative. It starts before the sine omega t signal. That's how I think of it. Leads by the angle theta, phase angle. The red, right here, they're trying to tell you that the red curve lags the dotted line by the angle theta. Essential identities. Go through it quickly. One thing about convention, this is probably the most important thing on this slide right here. It's just a convention. Sometimes you'll see expressions written this way, sometimes this way. So omega is always in radians per second. it's just people got a little sloppy with notation, and then they said, okay, we're going to make it convention. We think, a lot of times we think of angles in degrees, not in radians. So people will write something like this. They'll mix their units. Be careful about that. Just watch out for it, because people out there do it. That's the headline on this. Now, we're going to see Euler's identity. That E, Euler's number to the j theta, remember that we use j for the complex constant, equals cosine theta plus j sine theta. So I'm going to pick up here next time. I'm going to stop the video, and this will pop over to the next video.